How's it going, everybody? So today we're going to work on Chapter 7. Chapter 7 is titled Estimation. So let's go over some of our learning objectives. First and foremost, we want to become familiar with the concept of an interval estimate of the population mean, to understand how to apply formulas for a confidence interval for a population mean, to become familiar with students' t-distributions, to understand how to apply additional formulas for a confidence interval for a population mean, to understand how to apply the formula for a confidence interval for a population proportion. And one more, to learn how to apply formulas for estimating the sample size that will be needed in order to construct a confidence interval for a population mean or proportion that meets given criteria. So first off, we want to talk about estimation. Estimating is a population parameter by a single number is called a point estimation. So the statistic x with a line over it is a point estimation of the parameter mu, which happens to be the mean. This chapter deals with interval estimation. So here's the thing. So in the case of estimating a population mean, so figuring out what the population mean might be or could be, we use a formula to compute the data, a number E called the margin of error or the estimate, and form the interval. So basically what we're getting here is something called a confidence interval. And we're going to have a percentage that we are going to be able to say with this percent confidence, we can say that our mean will fall in this interval, okay? We do this in such a way that a certain proportion says 95%, I'm just going to move my video here, 95% of all the intervals constructed from sample data by means of this formula contain the unknown parameter mu or the mean. So here are some formulas here that we're going to work through. So basically for a large sample, and we know what it means for something to be a large sample, anything where your sample size is greater than or equal to 30 would be considered a large sample. So large sample, 100 times 1 minus alpha. And we're going to talk about what alpha is, but basically alpha happens to be the tail ends of a bell curve, all right? Confidence interval for a population mean. So for a large sample, we can say if the standard deviation is known, so the population standard deviation, not the population, if the sample standard deviation is known, then we can use this formula to determine it. And if the standard deviation, the sample standard deviation is unknown, then we use this formula. So you might be asking, well, what's the difference between this formula and this formula? Really nothing, other than the fact that this represents the sample mean and this represents the population mean. So they're going to tell you in the problem, is this, are we giving you the population mean? Are we giving you the sample? I mean, not the mean, the standard deviation. Are we giving you the population standard deviation, which would be S? Are we giving you the sample standard deviation here? Or what? So basically, this is our formula. So we need to calculate what E is, and then we're going to end up subtracting or adding E to a particular value, right? So the number E equals Z sub alpha divided by 2. So what Z is, we're going to talk about in a minute, but Z represents a Z score. It's going to tell us, well, what percentage of our values fall above or below our data, basically. So Z sub alpha 2 times the standard deviation divided by the square root of n, all right? Or, so and the only other formula here is just if we're talking about the population standard deviation, S, instead of the sample standard deviation. And then this would be called the margin of error. So I'm going to show you a few examples here, but I just want you to understand alpha. So all alpha is this would be our interval, all right? And we would want to say with, 95% confidence that our our sample mean would fall between this interval here. But what alpha represents is it represents the portion that falls outside of the interval, right? So when we say alpha divided by 2, we're just trying to find what the tail end is, only one tail end, and what the other tail end represents here, okay? And then, you know, this just goes further in that. So if we wanted to find a 95% confident interval, then we would say that alpha would be 0.05, so therefore alpha divided by 2 has to be 0.025, okay? So it's all we're doing is taking 95, we're subtracting it from 1, and then we're getting 0.05, and then we're dividing it by 2 to get these tail ends right here, okay? Okay, so right now we're going to go over 3 potential examples that you could see in dealing with these large or small sample confidence interval types of problems. So the first one happens to be a small sample, and the reason it is because of what's given here. So n is less than 30, which is 25, so therefore it makes it small. Known means that the standard deviation, the sample standard deviation is known here, so that's good. And we're looking to find a 98% confidence interval. So in order for us to do this problem, the first thing we need to do is refer to the formulas that were on the slides that we looked at, and we're going to want to write that formula out right from the start. So basically, how that formula is written is that the mean, okay, plus z sub alpha divided by 2 times the standard deviation divided by the square root of n. Okay, that's our formula. So given our formula, we can go plug in what we know. We know the mean is 12, okay, 12 plus the z-score. Well, for the z-score, this is one that I'm going to have to pause and go to a chart for, but first off, what we want to do is we want to go z to the, and we want to figure out what alpha is. Well, what alpha is going to be is alpha is going to be 1 minus 0.98, okay, which is going to be 0.02, okay, and then if we take 0.02 and we divide it by 2, okay, because that's alpha, then we can say alpha divided by 2 has to be 0.01. And then we're going to multiply this by our standard deviation, which is 1.2, divided by the square root of n, which is 25. Okay. So what we need to do now is we need to figure out what this value is going to be. We should be able to simplify this and this. Also, this should be plus or minus. Our formula is plus or minus here, because that's going to give us the interval. And essentially, what does this get us? This gets us what E is, what's our margin of error. Okay? So, but before, in order for us to figure this out, we have to go to a chart. So in your heads, what I want you to keep is 0.01, and we're going to find this on the chart and figure it out. Okay, so remember our value of 0.01. What we need to do is we're going to go to My Courses, and we're going to find the week that we're currently in, chapters 6 and 7. And if you scroll down, you're going to see 2 tables here. We're not using the critical values of t yet, but what we are using currently is a standard normal table. So if you were to click that standard normal table, what's going to come up is a PDF, and you'll see the little chart up here or graph that shows us that this table is going to represent the values that are less than z, where z is greater than. Okay, it's further to the right on the bell curve. This is not the chart that we want to work on, because remember, we're using tail ends. And so the tail end would be down here, and notice there's only a chart for the tail end to the left, which is fine. I want to know what both tail ends are here, but if I figure out one, then I know both of them. And what we're going to do is we're going to find that 0.01 here within these values. So if you look over here, you're going to find that 0.01 is going to fall somewhere in between 0.0102 and 0.0099. And so if you were to do this, you would line up the columns, and basically you would see that our value is going to be negative 2.3, okay, either 2 or 3. So negative 2.2 or negative 2.3, all right? Now, since we're in the middle, I'm going to pick a value right in the middle between 2.32 and 2.33, and that value right in the middle is going to be 2.35. Okay, so as you can see, I took that value that we just found, 2.3, and it was actually 2.5. I said it wrong, but if you go back, you'll understand it, 2.325, and now we're going to plug it in here. And now all we need to do is just do the simple math. And when we do the simple math, what we're going to get is 12 plus or minus, and the value that happens here when we go 1.2 divided by 5, because that's what the square root of 25 is, times this 2.325, we're going to get 0.558. Okay? Now, given that we get 0.558, remember that's telling us what our margin of error is. And so if our margin of error is this, given that our mean is 12, we will say that we have a 98% confidence that we are 98% confident that our sample mean will fall between 12 minus the 0.558, which is going to get me 11.4, and 12 plus 0.558, which is going to give me somewhere around 12.6 rounded. Okay? And so this is our 98% confidence interval. So now for this one, I'm going to go through this one a little bit more quickly. So in the same way, we know what E is. This is a large sample. It's greater than 30. We know that Z. So we're going to have the mean plus or minus Z sub alpha divided by 2 times theta, or not theta, I'm sorry, sigma over the square root of n. And so in calculating this one, we know that for this particular example, we have our mean being 30. So we're going to say 30 plus or minus. Since it's a 95% confidence interval, we can say that alpha is going to equal 1 minus 0.95, which is going to be 0.05, divided by 2 is going to be 0.025, right? So Z is going to be 0.025. And if we were to go ahead and take a look at that on the chart, we're going to get to that in a second, but 12 square root of 50, okay? Down here we're going to have 30 plus or minus. And now what I'm going to do is I'm going to jump to the chart right now just to show you one more time. So the square root of 50 is going to be 7.071, and we're going to jump to that chart right now. Real quickly, we're going to look at this and we're going to find 0.025 here, and we notice that 0.25 falls right here in this region. And so what I'm going to do is now go across, and I see that's 1.9 up top. I see the 6, so I'm going to use 1.96. And when we use 1.96 from the chart, after we've looked up 0.025 on that chart, we multiply it by 12 divided by 7.071. What we're going to get here is 3.326. And we can say that our confidence interval is going to be 30 minus this, and then 30 plus this. 30 minus it is going to be 26.674. Add that to 30, we get 33.326, and we can say that we have a 95% confidence that if we were to, select a sample mean, that it would fall between here and here. Now there's just one more question, and I have less than a minute to do it. So if I, if I drop off, then obviously, well, you guys can work on it on your own, but, I'm probably not going to finish this out. I'll leave this one for you to do, but at the end of the day, what you need to do here is we need to notice that it is large, but the standard deviation is unknown. And all the only reason I know it's unknown is because they're using S instead of sigma, okay? They're using S here. So what we need to do is just simply do the same formula and figure it out. Now, I will tell you that your confidence interval for this particular problem is going to be 57.9 and 58.2. 5.